folks. Welcome to
Vector calculus.
Alright folks, welcome back to the next lecture in vector calculus. Today we're going to be using an amazing tool called GeoGebra 3D to help us check out some of the amazing three-dimensional ideas we've been talking about, from points to lines to vectors and even planes. Let's start with the most basic idea, and that's of course a point. So I can just put a point right here, and you can see this point actually popped up right here in 3D space. I can move the point around in the XY plane, but I can also move it in the Z-axis. In other words, I can move its distance from the XY plane. So that's a pretty cool feature. Now, that's a point. How do you make a vector? Well, making a vector isn't as hard. All you have to write is vector, and you'll be asked to put a terminal point for your vector. So we can put, for example, I don't know, 4, 3, 6. So right here you can see the initial point of my vector is the origin, 0, 0, 0, and the terminal point of my vector is 4, 3, 6. What does that mean? Well, hopefully you remember from our lectures that our vector here has an x component of 4, a y component of 3, and a z component of 6. So you can see that right here. And as a matter of fact, we can even start annotating this. So that's pretty amazing. So you can see what we're really talking about here is that our vector goes 4 units in the x direction. It goes 3 units in the y direction. And you know what? I'm so fascinated by this, I don't even know where my y is anymore. And finally, it goes 6 units in the z direction. And so our vector ends somewhere right here. And as you can see, that's why our vector pops up right there. Alright, so that's really an explanation of a brief overview and review of what our vector components mean. Now we can go further than just vectors and points. We can even draw a line. Now many of you were confused when I said you need 4 equations for a line in 3D space, not just one, but now you can actually understand why. Okay, so here I'm going to give you 3 equations for a line, not just 1 or 2, but 3 equations. So let's see if this pops up. Now GeoGebra doesn't always cooperate with you, so don't worry if your equations sometimes don't work out. Alright, even me as an experienced GeoGebra am not the most apt at this. Anyway, here's our line in 3D space, and as you can see, we have the parametric equation of our lines here. Now, be careful. Even though this is the parametric equation, this above is the symmetric equation because it doesn't have any parameter. This one has a parameter lambda. You can see that parameter lambda right there. Okay, so we have both the symmetric and parametric equations. And if you want, you can even specify the line in a different way using a point and a direction vector. So let's say I want my line to pass through 10, 0, 6. Okay, whoops. Hopefully I don't mess up again. Anyway, let's say we want our line to pass through a point such as 1, 2, 3. Let's keep things simple. And let's say we want our line to be parallel to a certain vector, 5, 6, 8. So you can see our line actually passes through the point 1, 2, 3. Right? You can see our line actually passes through that point. And what's more, our line is parallel to this vector 5, 6, 8. And just to make sure, you can actually check. You can write the vector 5, 6, 8, and you can see that our line and this vector are indeed parallel. Okay, at least in 3D space. Now, some of you were asking me, hey, why can't we just define a line using a point? Well, this should answer your question, right? If we have another line passing through the same point, 1, 2, 3, we can have our line be parallel to a different direction vector. I don't know, maybe 10, 10, 4, right? Or maybe let's make it more extreme even. Let's make it 50, 10, 4. You can see that even though both of our lines pass through the same point, only one of them is parallel to one direction vector, right? They're both in different directions even though they pass through the same point B. Alright, so that's points, that's lines, that's vectors. How about planes? We haven't talked about planes. Well, remember the general equation for a plane in 3D space is ax plus by plus cz plus d is 0. And we can put that to use. Maybe I can put 3x plus 4y plus 7z plus 6 is 0. Okay, or you know what? Let's just set it to 0 for now. So here's our plane right here. And you can actually make a plane parallel to this. That's the challenge question. How do you make a parallel plane? Well, remember, if you want to create a parallel plane, you got to have the same coefficients. The only thing that can be different is your d value, your constant. So if I make my constant 40, for example, you can see that they're spaced out. My two planes are spaced out by 40 units, right? And as a matter of fact, I can even zoom out here. Now, what if I didn't want to make parallel planes? Well, then I could just, make this a different coefficient, and now you can see my two planes intersect. You can even see that they intersect at a certain kind of geometric object, which is a line. You see that line of intersection, hopefully. And that, ladies and gentlemen, that's it for this lecture on vector calculus. We'll check you out next time.
Embedded plus MKO plus scaffolding equals learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO, and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today. And the first 50 of you to use that link will get a 20% discount on the Brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.